We'll get to that a little bit later. All right, so now let's talk about the opposite. So let's switch for B, blue for base. So here we have our common bases. With the exception of NH3, what do they all have in common? Well, again, we have those AQs. But then what do these three have? I said to ignore ammonia, NH3, ignore that one. These all have an OH as the second part. So bases have an OH minus ion. That's what makes a base. So acids have an H plus and bases have the OH minus. And we'll notice I have sodium, potassium, and calcium. So then these are basically, we've got a group 1 or 2 metal with an OH. And that's what makes a base a base. That's why group 1 and group 2 are called the alkali metals and the alkali earth metals, because alkali means basic. So some bases, antacids, which stands for antacids. So like Tums is an antacid. All right, so just we're on page number 97 right now. And bases have a bitter taste. All right, so babies have evolved and humans have evolved really to not care for bitter tasting foods. So you're not going to find too many babies that like Brussels sprouts, but you're going to find a whole bunch of adults that like Brussels sprouts and cabbage. A lot of vegetables tend to be on the basic side, and most poisons tend to have a bitter taste. So that's why we have evolved to avoid some very bitter tasting foods, because evolutionary, we're trying to evolve to not eat poison, right? Bases feel slippery, and like a soapy feeling. So if you were to get even if you take some like baking soda and water, right, and you get that on your skin, it feels kind of like slippery, like you have like a soapy film on your skin. So that's a general characteristic of bases. So bases also are similar to acids, and strong bases are going to burn skin and burn holes in clothing. People tend to think that acids are like more dangerous than bases, but that's not exactly true. Bases can be very dangerous, especially because bases are going to react with the fats in your skin, and they're much harder to wash off than an acid. All right, so acids and bases are both electrolytes. And again, electrolytes conduct electricity because they have mobile ions. And what does that mean? Right? That means they ionize or dissociate in water. Remember, electrolytes, acids, bases, and salts. Right? Abs, right? Electrolytes give you abs, acids, bases, salts. And remember, a salt, ionic compound, metal plus a nonmetal. So the greater the concentration of ions, of course, will be more conductive. And weak bases are weak conductors. Strong bases are good conductors. And our bases react with acids, right? Acids react with bases, bases react with acids. All right, so then forming neutral solutions. This is very similar to what we just wrote about acids, so I'm going to go a little bit faster. Okay, this is a double replacement reaction called neutralization. And let's use our HCl plus NaOH again. right? So then acid part, base part. H plus for the acid, OH minus for the base. So H and OH make water. So acid and a base make salt. Remember, this is only one salt, right? This is where sodium chloride can come from, right? We can create sodium chloride by reacting an acid and a base. So here's another acid and a base. So this is an acid. How do I know it's an acid? Because I've got hydrogen with that group 17 bromine, right? There's that H plus. How do I know that this is a base? This is a base because I've got the OH minus. So the H goes with the OH to make water. And then the calcium goes with the bromine. So Ca goes with the Br. Now let's be careful. When I'm writing a formula, I have to make sure I'm writing a correct formula with the correct ratio between the two elements, which is based on their charges. Calcium is a positive 2 charge because it's in group 2. Bromine is a negative 1 because it's in group 17. So then now calcium bromide. Now let's work on balancing this neutralization reaction. So I'm going to actually switch to a different color. I'm going to switch to yellow since it's now neutralizing. So this is why we write the HOH, right? Because this is the OH minus and that's the H plus. And so from our balancing equations, we can use that polyatomic ion trick, right? If the OH over here stays the OH over there, I can treat it like it's a group. So I have 2 OHs on the left-hand side, but only 1 OH on this side. So I have to make this 2 OHs. But now I have 2 H's. So now I need to make this H also equal to 2. So I'll put a 2 in the front. And so now I have 2 bromines and 2 bromines. And so it all works out nicely in the end. And if you like placeholders, you can put in a 1. All right, continuing on. Bases cause acid-base indicators, right, like a pH paper, to change color. So litmus paper, right, is going to be blue in a base, right? B for blue, B for base. And we've got this thing, phenolphthalein. Acid-base indicators are on table M of your reference tables, and we're going to talk about them in a separate lecture. So now we're almost done. I've got this picture again. So now bases have our pH values greater than 7, and they fall on the high end, right? A comes before B, so lower numbers to higher numbers. So remember, our acid ion is this H plus, right? This is our acid ion. So in our acidic range, right, from 0 to 6, right, we have a large H plus, and we've got a really, really, really small OH minus, right? Little itty bitty bit of base, right? There's always acid and base present at every pH value. So our neutral here, our H plus equals our OH minus, right? Water, HOH. So now in our base range, right? Here's our base ion, right? So our base ion over here. So then in our basic range from 7 to 14, right, we notice that we have our OH minus increases, right, from 7 to 14. And our H plus decreases. So in our basic range, we have a very large OH minus concentration and a very small H plus. So as pH increases, OH increases, but H plus decreases. It becomes less acidic. So we can refer to anything. So our general formula, again, we're going to just skip that. And we're just going to talk about a little bit of review. All right, so what exactly is a salt? A salt is a neutral ionic compound that has positive ions other than hydrogen. because the H plus is going to mean is an acid. And if we have negative ions other than that OH minus. Okay, so examples of salts. If I have lithium and bromine, right? Lithium's a metal, bromine's a nonmetal. Potassium iodide and calcium chloride. And I'll use a polyatomic ion, sodium nitrate. All right, salts are formed from that neutralization reaction. And they are neutral. So an acid plus a base makes a salt and water. So if I have the acid HBr and I have the base lithium hydroxide, an acid and a base make a salt and water. Where's the water come from? HOH, right? So HOH for the water. Now I need the salt, right? These two get together, lithium and bromine. Lithium and bromine, group 1, group 17, +1, -1, all set. All right, we're going to spend more time on those reactions later. Right now, the most important thing that we need to focus on is the H plus is the acid ion. The OH minus is the base ion. And then the acid has a low pH and the base has a high pH because of the presence of what ions? Remember, electrolytes have those mobile ions, and acids, bases, salts. So acid, base, and salts are all electrolytes. Right, so lemonade, right? It's got an acid, right? Citric acid. And then in solution, of course, right, which means AQ. So why does this light bulb light up if we put it in salt water and we hook up a battery to it? Because we've got mobile ions. Okay, that's what makes those solutions. All right, so one more page, I believe. Okay, so now we're going to talk about our acid-base theories. Okay, so we have something that's called an Arrhenius acid. This is just some guy's name, so don't worry about it. So Arrhenius acids, right, contain H plus as the only positive ion in solution, right? That's what made an acid, the H plus, right? We can call that the hydronium ion, which is H3O plus on table E. Because when that H plus is in the presence of water, it's going to join up with that water to make HOH, H3O, sorry. So here is an example of an acid. Why is an acid, right? It splits into the H plus and the Cl minus, right? So then this, what we say, ionizes, right? So here's where the electric current can go between. So then the strong acids dissociate 100%, right? That means they have more of that H that makes them stronger acids. So the general rule for the acids is you've got your H plus in the front, which is the H3O plus. And we're going to call that the hydronium ion. That's an M, hydronium ion. So not all substances that contain hydrogen are acids. Water is HOH. It's not an acid. It's technically equal acid, equal base. Methane, which is CH4. This is why we do organic first. This has hydrogen, but it's not an acid because it's not. Glucose has a lot of hydrogen, C6H12O6. It's not an acid. Hydrogen peroxide is H2O2. It is also not an acid. And ammonia is NH3, also not an acid. So, right, be very careful. Acids are listed on table K, and they have the H plus is the only positive ion in solution. So now let's talk about the hydronium ion. Oops, meant to scroll page. All right, so the hydronium ion. So when hydrogen, which has a mass of 1, atomic number 1, it has 1 proton that's positive and 1 electron that's negative. So when it becomes an ion, the H plus, right? Remember, the positive means you lose an electron. All that's left if I lost that electron is a proton. So thus, the positive hydrogen, right, or our H plus, is essentially just it is a proton. But when this proton, right, which is this tiny little, very positively charged little particle, is in this H plus ion, right, so that proton is very naturally attracted to the unshared electrons and that slight negative charge of that oxygen in the water, right? So look at all these, these are electrons that are negative, right? So here's this negative electron, and here's this really positive, and these things are going to be attracted to each other, and then it's going to form this H3, right? 1, 2, 3, H3O plus. And then this is what we call the hydronium ion, right? The H3O plus. And then that's listed on table E. So whenever you've got that H plus, so the H3O, so according to this Arrhenius theory, right, the properties of acids, right? Remember, acids have that H plus, right, which is essentially this H3O plus because it's in the presence of water, are functions of this hydronium ion. Remember, function has to do with math. We're going to get into some math a little bit later, but we're not doing functions, but just function just means math, right? So that means the more H plus there is, the more acidic, right? That's mathematical, right? Larger H plus, the more we got, the higher the lower the pH, right? The more acidic. Okay, so now we're going to have to talk about bases according to this Arrhenius theory. Righties, and I guess my eraser doesn't want to work. All right, so we have an Arrhenius base. So we have this water solution that produces the OH minus, which is a hydroxide on table E, right? So table E, right? And our bases are on table L. I want to make sure that we talk about our acids. Our acids, right? Our acids are on table K. Just want to make sure you're always referring to tables K and L every day, all the time in this unit. So if the acids have the H plus as the only positive ion in solution, bases have to be the complete opposite. So bases have the OH minus as the only negative ion in solution, right? H plus, only positive ion. So now OH minus, only negative ion for the base. So a base is going to have an OH at the end of the formula. Notice how I did not say the beginning of the formula, the end of the formula. But not all compounds that contain OH are bases, right? This is why we did organic before we did acid base, right? Because we had what had an OH in organic? Alcohols. So alcohols are not and organic acids. There's only organic acids. There's no such thing as an organic base. I know, isn't that weird? Okay, so carbon can only form acidic compounds. Okay, so here we have organic acids. Alcohols are not bases, even though they have an OH. So water is HOH. So water is neither an acid or a base. Water is neutral because it has equal HOH. So it's actually both amphoteric, right? That just basically means it is both an acid and a base. Methanol is an alcohol. So, right, that methanol, one carbon, so CH3OH, that OH is not a base OH. That's an alcohol, right? So careful. No alcohol is not a base. All right, and then methanoic acid, right, which is one carbon, and then that COOH is not an OH. So not a base. There's no organic bases, right? So then that is going to wrap up our acid base. I just want to quickly, why do I always do that where I want to do that? Quickly write down here at the bottom, again, right? So I'm going to switch over colors. So our H plus is an acid. Acids are located on table K. And so then now I'm going to add them together. Let's use green. We'll add these together. And we're going to have a base, which is our OH minus, which is the hydroxide, which is the base. This is listed on table L. All right, so we have our acid and our base, table K and our L, our hydronium ion and our hydroxide ion. So now these two things get together and they yield, right, or produce acid and a base, make a salt and water. So then we have H plus OH makes HOH, neutral. So they neutralize each other. Okay, so acid and a base make a salt and water. And one quick more thing, I just want to quickly write in here. So the acids have a low pH, right? Less than 7. Our bases have a high pH, greater than 7. And what about our water? Neutral. Our H equals our OH. So then that is why we have a pH of 7. And I like how I ended that with those 7s. All right, that's it. And we're going to delve into some alternate theories on acids and bases, because this focused on our Arrhenius theory, which is just named after some guy. Savante is actually his first name. All right, until next time. All right, go back and review your notes often.